So welcome all to Women Who Code San Francisco, our first mock interview for the year 2021. And today I'm joined by Gabriela Martinez. Hello, Gabriela. And
Hello. Hello, everyone.
And today's session will be a mock interview on sorting and searching. The Women Who Code San Francisco group has been diligently working on sorting and searching this year. And to culminate just to mark the end of that study session, we have this mock interview. So I always love to introduce our rubber ducky, Ella. And we're going to be rubber ducking with Ella today as we go to this mock interview. We will solve two problems today. So the first one is going to be merge k sorted list, and the other one is kth smallest element in a sorted matrix. And we will take turns doing this. So for the first round, Gabriela will be the interviewee, and I will act as the interviewer. Please excuse the sound of the dog. He sometimes talks to me. So all right.
It's a good background sound.
Yes. And so with that, I am going to open up our merge case sorted list. And this is the problem. Okay. And Gabriela, the way I will start this off is I'm going to just read the problem to you. And so this is merge case sorted list. The description of the problem is you are given an array of k linked list. Each linked list is sorted in ascending order. Your task is to merge all these linked lists into one sorted linked list and return it. So we have got some examples here. So if you have a list, which is 145, 134, and 26, the output should be these values. You can see that they are presented in sorted order. And you have to merge them into one sorted list. And we have another example. If the array is empty, you should just return an empty list. And likewise, if the array has a single list and that single list too is empty, just return the empty list. So these are some of the test cases.
Perfect.
We also have some constraints where k, the number of linked lists is equal to the list.length. And you could have, like, as I've mentioned in the use case, you could have an empty list. Now, also note that each of the elements in this list is in ascending order. That's something to note and something to keep in mind when you are presenting your solution. Do you have any
questions? Well, yeah, I think the problem, the description is very clear. Yeah, the only thing that I maybe could ask is that if there are negative numbers in the input, or we have just positive numbers. In that case,
that is a good question. Now, from what we are seeing is each of these elements in this linked list, they could be negative. So it does specify here that list each of these elements in this list, those values could be negative. So yes, you could have negative numbers. So
okay. That's good. That's good to know. Yeah, well, I see that we can have empty list and empty elements, and okay, I think Yeah, and only numbers and integers. Okay, so that's the definition of the nodes. So yeah, I think I don't have so far I don't have more questions. So I think I have enough information to start thinking about a solution.
Okay, excellent. Now, for a whiteboard, you have two choices. You could share your screen and you know, you could actually perhaps use the area here to whiteboard out your solution if you want to.
Okay.
Or you
Yeah, I think I can share my screen. And if you can share the link of the of the problem, I can start sharing my screen and start typing the
sure.
code of the solution. So I think kind of start from there, and I'll let you know when I'm ready to share my screen.
All right. So I just sent you the link.
Thank you.
Of a chat. Okay. And I'm going to stop sharing now and turn this over to Gabriela.
Thank you. Okay, so I will start sharing. Do you see the problem?
Yes, I do.
Okay. Okay, so I see that the lists are sorted. So and the requirement is that the output list should be also sorted. So that's something that we should keep in mind, that that the output should also be in the ascending order. And I also see that there is a linked list or a single linked list. And in my case, I would like to use C# as a language that I feel more, I think I feel more proficient in C#. So that's the one I would like to use for the implementation of the solution. And okay, so one thing that I would like to start talking about the solution is, like, what could be the brute force solution? Like, what would be the simplest thing to do if we want to solve this problem? And one thing that I think I can start like in a like pseudocode, like what are the steps that we need to implement in order to solve this problem, is we need to traverse all the list and make one big list with all the numbers that we have in all the lists in the arrays, and then we can sort them. We can sort all the numbers and have the resulting list. So that would be like, if we were to solve this problem manually, that would be the steps that we need to follow. So so for example, if we're thinking that what could be the time that would require to do these three steps that I mentioned, which the first one is merging all the numbers in the lists, and then sort them again, because if we merge them and if we don't do the sorting, or we just merge them in the order that they are, then we need to sort them. And again, we just have to recreate the list that we have, or the single list, and return the result.
Right. And then prior to merging all the numbers in the list, you would also have to iterate through all these nodes.
Exactly.
The value.
Yeah. So for example, for this case, this would be the brute force solution. That's the yeah, the more easiest or to implement, or the steps that we need to do for doing this, like if we were doing this manually.
Right.
But let's think about what would be the time complexity for this.
Very good.
And
Mhm.
for example, for merging all the numbers, if we have, let's say that we have n nodes in total, so we will have to traverse, and then the time complexity will be big of m, because we're going to traverse all the nodes, and then we need to sort. And for the sorting, let's talk about any, or like a regular algorithm for sorting that would require, let's say, a big O of log n. That would be the second case, the second step. And then again, we will be recreating the list. So the third step will be, again, big O of n. So this at the end will be n, because we said that we need to traverse, and then log n for the sorting, right? And but what if we have a very long list, and in the if we increase the number of nodes that we have and all the list, this time will be increasing. And so it will be like very optimal to do the sorting. If we already have the list sorted, we are not taking advantage of that in the merging. So we need to do something, or we need to implement a solution where we take advantage of that, of the list that are already sorted. And in the same iteration that we are traversing the list, we can merge them in the order that they are already. So for that, we can implement a different solution that can take advantage of that, and that's the merge of the two. It's a combination of a divide and conquer approach, and taking into account that the merging, it's can be done in the same way that we are, like when we want to merge two two lists, for example. So that's, I would say, is the merge part. So in this case, we will be, instead of using this log of n, we can implement a solution with, instead of traversing all the nodes and sorting after, we will be traversing the number of, let's say that k is the number of the count of lists that we have. So we can improve this time using the divide and conquer approach. And so let's see what are the steps that we will have to implement. So the first thing will be traversing the, let's say if we have the list A, B, and C, we will be taking two of these lists and merging them. So I will take A and B, and then we will get the A as a result. And then this list A, and then the other list, which is C, and we will have one list, and this will be already sorted. So this is the approach that I think will be more efficient. And I think that using this approach will require, instead of traversing all the nodes, in the worst case, we will traverse just 3 times, for example, in this case, 3 times the number of lists that we have. So I think that this will be translated to n log of k. Oops, sorry, I think I need to admit. So okay. So I think this could be a good solution to implement. So I guess we can take this approach and see how this will look in code. So the first thing that we need to do is the number of lists that we have. We need to take only two or divide them. What I want to achieve is take in pairs and then merging them until we have just one list. So the first thing that I will be
Gabriela,
implementing.
if I could just interrupt you. So
Sure.
I want to just backtrack to your steps. So you have, you start off with an example where you have 3 lists. You have A, B, and C. So in this
Right.
case, K is 3, correct? Because the count of lists is 3. So
Yes.
yeah, I guess it does correspond to this first example 1. And then you said
Right.
you would first merge A and B together. So
Right.
when you're going to merge A and B together, the
Yeah, the resulting list will be just one list.
okay.
So we will be
Mhm,
having just one list. So I just for a convention that just to have this this convention of having perhaps the left list as the result of both. So
mhm,
this will result in a just one,
mhm.
which is A, let's say, in this one, but this will be containing, of course, the nodes of A and B.
Right. So you are effectively merging 2 sorted lists then
Uh,
at a
Right.
time. Okay.
At the same time that we are traversing the nodes. Instead of first doing the traversing and then resorting, we are going to do the traversing
Mm-hmm.
as well as we are doing the
Oh,
merge, the sorting, but the merge, but keeping the sort into account with the resulting list.
okay. So depending on how you merge your 2 lists, you're going to get a time complexity depending on how you choose to merge the 2. Right?
Right. Yeah, because instead of traversing every list,
Mm-hmm.
the whole list, you will be traversing the list and merging them. So it's more efficient at the end of the algorithm, because in the moment where you finish with the smallest
Mm-hmm.
node or the smallest list,
Mm-hmm.
then you can move to the next one, and you don't have to traverse the whole list, because we have a single link list.
Mm-hmm.
So we know that the last pointer that we have in
Mm-hmm.
the previous list, we just have to point the last one to the next one.
Mm-hmm.
And that instead of traversing or inserting,
Mm-hmm.
we just link the list, and that also makes
Oh,
the algorithm more efficient.
okay. And the last question I had, it is for this for now, was what is the time complexity that for this merging of the two lists that you're looking at? So,
I think it's the same as using the merge sorting method.
okay.
And because what you are doing is divide the whole array or the whole list in parts, and then every time, for example, if you have, let's say that we have 8 elements. So we have 1, 2, 3, 4, 5, 6, 7,
Mm-hmm.
and 8. So the first thing that you do is you split this array into parts. So you will have 1, 2, 3, and 4, and this will be the left. And then you have the right part, which is 5, 6, 7, and 8. And then you will be doing this iteration again, and instead of splitting 8, you will be splitting two lists of 4 elements. So you will have for the left, you will have 1 and 2 and 3 and 4, and this iteration. And then in the next one, you will have 1 and 2, and the last one. So in this case, for 8 elements, we have 3 iterations, right? So we needed to do this 3 times. So the number of operations that we needed to do were 2. In this case, we had 8 elements. So we had 2 power of 3. So this is the log of, this is the log of, log of, and log of, how can I say, log of 3. So this is a complexity of the merge, the sort merge sort algorithm. So it would be the same for this approach using the divide and conquer, and yeah, it will be faster than using the brute force solution. Okay, so I think we're gonna start by coding the solution.
Yeah, go ahead.
And so the first thing is that we have the array of the list array, and like I was doing in this example is I'm going to divide, or I'm going to split them into parts, and we will be doing that recursively with the rest of the list, the left part and the right part, and then we'll be merging 2 lists only to have just one. And so the first thing that I would add here is having a method where I can split the list that we have, and using the recursion, and also I will be using this merge sorting method. And so the first thing is this will be returning a pointer to the starting of the list, the result of the list, which be sorted list, and this will be merge list. This will be this method, merge list, and this will be receiving the list of node, the array. And also we have to know what is the index of the starting, or what is the left part, and what is the right index in the that we're going to merge. Because we have, for example, 3. In this case, we have 3 lists, like in the example number 1, and we need to know that what is the index that we're starting to do this divide. So I'm going to have this start, and then I'm going to have the end. So this will be checking, or checking what are the indexes that we need to split the list. So so the first thing is, what is since I'm going to be calling this method recursively, the first thing that I need is to know what is my base case. So When start and end are the same, that means that we have the both indexes in the same position. So that means that we have finished of the merging, the merging part. So, and then in that case, what we are going to do is I'm going to return the first position of the array of the list, because that's the one in that, like in this example, when I was merging A, B, and C, and the solution is going to have all the nodes merged in one. So it's going to be in the first position of the array. So that will be the list that will be getting all the nodes sorted. So that will be the returning value. And then what we need is, if we are not in the if we're not in the same position, if we then that means that we need to split in two parts. So we have the start and the end, and what we need to know is what is the middle point, or the mid index where we need to divide and know what is the left part and what is the right part. So we need to know what is the middle point, and this middle point will be starting, or we have to calculate it with the start. And let's say if we have the first element is 0, and then the last element in this case it's 7, because we have 8 elements. So the mid part will be the start, which is 0, and the end, and divided by 2. But we also need to consider that is the starting part, every iteration, the starting part also will be moving to the right, because we are going to be having less elements in the list. So we are going to also do n minus a start to consider that, and moving also the number of elements in the middle part. And so I'm going to do this calculation to have the midpoint, and so that will give us to now doing the merge, because I'm having now two lists or two pointers, which is merging the list. And let me see. Yeah, we have the list, and I have the start. So the left part, this is the left, which is the first part of the list, and I have the left part, which is the pointer is at the start, and then the other part is where it's ending is the mid pointer, and the right part, I'm going to call it right. I'm going to merge the list from the mid part plus 1, because we are not going to include that because it's in the left part, so it's mid plus 1, and the end until the end pointer. Okay, and in this case, okay, so it's merge list, because I'm going to be calling this method. And okay, so so now that I have the two lists that I want to merge, I'm going to call my method that is going to be actually doing the merging part. So I'm going to do the left and the right, because I have already divided them. So instead of having all the lists, I'm just going to have two lists, and I'm going to merge them here. And that's the part where we are going to return that merge that we have in one And these two lists that we are merging in one, that's the result of the sorting list. Okay, so I'm going to add this method that is going to be doing the merge, and it is going to receive the list, let's say A, and then the list that it's B. So we have the two lists, and we're going to traverse them. And if I have one number that it's smaller than the other, I'm going to merge first the smaller one and then the opposite. So I'm going to be checking which one to merge first. So we have, since we have this single list, linked list, I need to have one pointer to the new head of the resulting merging list. So I'm going to write. I'm going to have this zoom head to keep the pointer to the first node. So the first node is the node A, and also I need one pointer to have the current node that I am traversing. So at the beginning of the algorithm, both are going to be in the starting part of the starting node. So I'm going to initialize them in the same value, and then I'm going to be traversing A and B. So while I have nodes in A, so if I have A different than null, and also B is different than null, I will be keeping the traversing. And then I'm going to ask if my left, or the first A list node, so in this case is A, and the property that we have, the value is val, and so if this one it's smaller than the B node, that means that my current node should be point first to the node that it's in the list A. So the current node, the current pointer, is going to point to A, right? And then I'm going to move to the next node in A because we already merged this one. So I'm going to move the pointer to the next one, right? And if the opposite happens, or the node that it's the smallest is the one that we have in the list B, then I'm going to do the same, but with the node in B, right? So we're traversing both lists, and okay. But what if we already finished with one of them? Okay, so okay, and also I need to move the current pointer. Okay. So if we already finished with one of them, but the other is also having some nodes that are remaining in the list, we need to add them. We don't need to traverse them, just we need to point the last element to the one that is remaining. So I'm just going to check that if A is still, it's not null, that means that then we finish B, but we still have some elements in A. So that we just need to have the current, because that's in the last node, just pointing to our
Yeah.
pointer in the list A, because that's
Mm-hmm.
the one that has already some elements remaining.
Okay.
And in the case of the
I could just interrupt here.
sure,
So I do see, so here we are merging two lists, A and B.
right,
And here, so we have a dummy head. So
right,
my question for you is, let's say you had the list A and B, and
Right.
A has elements 2, 3, 4, and B has elements 1, 2, 3. So what I'm trying to say is that the first element in A is actually greater than the first element in B. So if you have the current way that you have it coded, so dummy head would be equal to A,
Right.
would be equal to
Yeah, but we are going to return. I think. Yeah, I think I understand the question. So instead of yeah, what I'm going to return is the dummy head dot next,
okay.
because that's the one that has which is the starting of the
Oh,
list.
so that is just a sentinel, like a throwaway value.
Exactly. Just to keep the pointer, and because since the other one, since we don't know which one is going to be first,
Right.
then the next pointer is for the actual starting node, because we don't know if it's going to be A or B.
Okay, got it. Very good.
Right. Good point. And so yeah, so if the remaining elements are, like I said, in B, then what we are going to do is keep or link them to the last node that we have in the merge list. So
Mhm,
that's the one that we are going to return, and that would be the merging part.
mhm.
So how do we call this method? And I think that's the part that we are missing, and that I am missing. And so since the first time we need to traverse the whole array, so I'm going to call the merge list method, and I'm going to send it the whole array, and I'm going to start, of course, in the 0 position, or in the index 0, and I'm going to start in the last, and I'm going to end, because we're starting in the length -1, because we're with the 0 index. In C# we have 0 index, and this is the value that we're going to return. And since in this case we're using, we have it's possible that we have an empty list. We need to check that the list is not null, or if we have no elements, or if we have just an empty list, we need to know the length. And if this is equals to 0, in that case, we're going to return an empty list or null, because we don't have elements to merge.
Yeah,
And
we'd like to return an empty list. So whatever you do in C# to return just an empty list.
right,
Mm, yes.
I think that we just an empty. Let me see. Yeah, it's a new list node. Mhm. That's the thing we're going to be returning.
Right. And I think just the check on the previous line is if list is equal to null, you want to.
Ah, yeah, you're right. Thank you. If that's what we need to check. If list is null, or if the length it equals to 0, then we need to return an empty list.
Mhm.
Okay, yeah, I think that's true. And let me see if I missed anything before trying to run the code. And let's see, I think we can run the first code, the first example, and see if we have any errors. But let me see, let me try to just double check the code and see that there are no syntax error or something that could be causing an error.
Mhm.
So this merge is left and right, and then we have this method, which is the merging. And I think I don't see any typo. Seems that that's fine. And F, it's not null. B, it's not null. Okay. Okay, so I think we can try. we can run the code and see if that's solves the problem.
I think we have
Okay, I think I have a typo, right?
the length.
Length is the TH, I think.
Mhm.
And it's also here.
Yeah.
Sorry. Okay, so I think that's it. And let's take, okay, let's run the code. Okay, let's start for the result. Oops. Okay, so I guess something it's causing oops, and a time limit exceeded. That means that maybe something it's causing like the recursion, perhaps it's causing the time limit.
Mm-hmm.
Though
That's fine. Just in the interest of time, could you just walk us through the time complexity?
Yeah, sure. Okay, so at this case, in this, we're since we are using recursion, so every time when we are using recursion, every time we do this split or this divide, we do this, like I said, the log of, instead of doing log of n, we do this log of the number of list.
Mm-hmm.
And I think it's also, so it's going to be n, which is the number of nodes log of k.
Mm-hmm.
K instead, in this case, it's n is the nodes and k is the number of list.
Mm-hmm.
So the time complexity will be n, because we're traversing, in the worst case, we will be traversing all the list.
Mm-hmm.
And the sorting or the merging will be log of k. That's the time complexity. And the space will be, this is the time, and the space complexity. Okay, in this case, we'll be using the same.
Yeah, it is in place. Mm-hmm.
So it's constant, is a constant space, like it's just
one.
one, or yeah, I think.
If you because you are just modifying these lists in place, right?
Right, we're not using any additional space, so yeah, it will be constant space.
Okay.
I think.
All right. Okay.
So
We are almost out of time.
yep.
So, but this was a good attempt, and you explained the problem very well. I would just ask, if you could scroll towards the bottom, and so
Right.
when you're merging these, merging to a linked list, what is your time complexity here on this one?
In the
So
merging.
if you have A has M nodes and B has N nodes, what's our time complexity on this one?
In this one will be M plus N,
Yeah.
I think.
Mm-hmm. Yes, that's good.
Because it will be because we will. Okay, I think so. I mean, but
it is M plus N because you are iterating through them, right? So
right, that would be the, yeah, you're right. Yeah, that would be the worst case. Right.
Yeah.
Mm-hmm.
Okay. All right. That is very good. At this time, Monica, I would
I think we
like
can.
for us to just take a little pause in, and so that we can just do a time check.
Yeah, let me pause the recording.
Yes.
Okay, so I will take over. and I will share my screen. Let me just open the question and I will be sharing in a bit just to get ready the screen. Okay, so hi, Daniela. So I'm going to share with you this problem that we are going to, we will be trying to solve with you. And this is called a kth smallest element in a sorted matrix. So this is about that given an n by n matrix where each of the rows and columns are sorted in ascending order, return the kth smallest element in the matrix. So note that the kth smallest element is not the kth distinct element. So this is a very, very important thing to keep in mind because it's sometimes could be confused, but what we want is the kth smallest element. So let's take a look at this example. We have we have this matrix 3 by 3 elements, and we have this list which we can have in one sorted list together, and we need to get the eight um, smallest element in this sorted list. So in this case, it's 13. Okay. And then we have the other example where we have just a matrix again by n because it's a square matrix and it's just one element. So in this case, just we have one element, so k is equal to 1, and the returning or the result is this -5. And there are some constraints that you need to just take into account, that n it's equal to the length of the matrix in this case, and we have also the same for each row of the matrix, and we can have up to 300 elements. Okay. So 300 by 300 because we have an n by n.
Right.
And the numbers that we can have in this, like the numbers in this matrix, we have negative numbers, and we have from 10 up to power of 9, positive and negative. Okay. And it's guaranteed that it's going to be sorted. All the rows and columns are guaranteed to be sorted. And so you can, and k also, the constraints are that k can be between 1 and n quadratic. Okay.
Right.
Because could be the last element, because we have a matrix where we have n by n, so can be from 1 to the last one, which is n cube. And you can pick the language that you feel most comfortable to make the implementation of the solution.
Okay.
And I guess I can share the link as well with you to so you can open that and you can share with us the.
Sure.
I'm going to share it with you. I'm going to share it also in the chat. So if someone else want to open that in their machine. So I already sent the link. Let me know if you can open it.
Sure. I'm going to share my screen now. Let's see.
Okay. Sure. Go ahead.
can you see my screen?
I see it.
Okay, good. All right. So we have a sorted matrix, and we have to find the kth smallest element in the sorted matrix. So this is an n by n matrix. Okay, got that. And this matrix will have at least one element. Okay, so.
Right.
So I would like to use this area here as my whiteboard, if that's okay.
Yep, that sounds fine.
So as I'm reading through this, I see that it says we want to find the kth smallest element in the sorted matrix. So always when I see the word like kth smallest element, what comes to mind is the use is a heap. Because with a heap, the heap gives you the ability to get like the smallest element, or you can actually look up the smallest element if it's a min heap in O1 time. That's what just look up. And of course, for insertions and deletions, it's O log n. And so I also see that we just want the kth smallest element. They're not talking about sorting this entire matrix, right? So just let me just walk through a couple of use cases to make sure I understand this. Oh, admit. Okay, so here we go. So I have this. I'm just going to expand my test cases, and perhaps, yeah, let's keep it simple. So we'll do something like I'll add 16, 17, 18. And so if k is equal to, let's say, okay. So let's say if k is equal to 10. Oops. If k is equal to 10. If k is equal to 10, then the kth smallest element would be 16. I could also have negative numbers. I could have -2, and I could have here 4, I could have 7. So I also know that as per the description, it's not only that the rows are in ascending order, the columns too are in ascending order. So I'm going to put this down like this. So I'm just going to put this here. So I just have this as a, oops, have this as a reference. Okay, so the kth smallest element, k is equal to 10, the kth smallest element will be this. Okay, so -2, 1, 10, 12, 4, 5. So these are the sorted columns as well as you have sorted rows. All right, now we also know that this is an n by n matrix. The maximum value of n can go up to 300. So the total elements can be up to, so 9, 1, 2, 3, 4. So we can have about 90,000 elements. In the worst case, you can have 90,000 elements. The range
Right.
from 1 to about, the count is going to be this much. Okay, all right. So just like the brute force approach, brute force approach would be to just merge all these elements together into one big list. So kind of just like flatten it all out. So we'd have like -2, 4, 7, 1, 5, 9, and so on and so forth. And then we could heapify it, put it in a minimum heap, and then just keep getting the minimum element of this heap. And I would just make about k iterations, oops, k iterations to this heap. And however, there are some drawbacks to that approach. So we'll talk about that in terms of the time complexity. First, let's talk about space complexity. So if I go and just flatten this out, this two-dimensional, this array out and just into a single list, I'm going to need additional space. And so the additional space will be O, because I'm going to have all these elements in this. So it's actually going to be, total elements is going to be O(n squared). So I need to have all these elements in this list. So that's my space complexity.
Yeah.
Time complexity would be, now, in order to I've mentioned here that if you want to just pop off the minimum element from the heap, the time complexity is log of n. But if I want to get the kth smallest element, right? So it'll be k. So in this case, I said log of n, but this is really where n is the number of elements. So what's going to happen here is, so when you say log of the number of elements, we have really got a lot of elements here. So it's actually log n squared. And then we got to make k iterations to it because, oops, we've got some more people joining. So we got to make k. Okay. We have to make k iterations to this minimum heap, right? So you're looking at the time complexity of k times log n squared, which is not desirable, especially when we look at time complexity. You would prefer to get it, the best case for space complexity, it would be O1, ideal. And for time complexity, we prefer not to have any polynomial forms like this. We would prefer to have it like O of n or something like this, or maybe O of log n, be better. So this solution clearly would not work. So let's think about how we could optimize this and come up with a more efficient solution. All right. So in order to do that, I'm going to read through the problem again. So we know we got to find the kth. Okay, we have people joining. Okay. All right. So here we know we got to find the kth smallest element. And here we want to use the minimum heap. Just as a quick refresher, when you think about heap, the heap is actually a specialized binary tree. And in one of our prior presentations, I did mention the different kinds of trees. When we talk about the heap, the way it's implemented, it's a complete binary tree. So in a complete binary tree, every level is filled, except the last level where all the nodes are to the left. And what this gives you is the height of this binary tree is going to be log of n. So to basically to traverse from the root node to that last node in the binary tree, in this complete binary tree, it's going to take you log n time. So that's where we actually got all this log n.
Okay, Daniella, sorry, I would like to pause, make a comment. So you mentioned that the heap is like a binary tree or a complete binary tree, right? And so the height of the binary tree, how could you explain? How do you know what is the height of a tree?
Right.
Like, Can you elaborate a little bit?
Sure. So the height of a binary tree is calculated as the number of nodes from the root node to it's the maximum of the depths of any of the nodes in the tree. So that would actually come down to, if you were to pick any node in a binary tree, the depth of the node is the sum of the number of nodes from the root node to that node, but not not including that node. So you're basically going that way. And as far as the height of the entire tree goes, it's the maximum of the depths of all the nodes. So basically you want to get to the node that's at the lowest level, and you want to get the depth of that node, that becomes the height of the binary tree. And we know that just the way the binary tree is laid out, with each level, you are actually halving the number of elements. So if you kind of were to walk up, you actually kind of halve the number of elements. And you talked about it a little bit with your merge, right? You were splitting and
exactly.
Yeah. So like if you had, to give you an example, if you had like 8 nodes, you start off with node 1, then you have 2, 3, 4, 5, 6, 7 to just give you a visual, and then you have 8. So you could just kind of break it down that way, where you're kind of, and that's how your
Okay. Thank you very much for the explanation.
Yeah.
Got it.
Okay. So here now we have this, and so I was again reading through this. We talked about, okay, so the minimum heap sounds like a really good idea, but perhaps there's something here that we can use to improve on our complexity. So we're given an n by n matrix where each of the rows and columns are sorted in ascending order. Now, so each of these elements are being sorted in ascending order. So they are sorted. So how can we use this information to improve on our time complexity? So let's take this. Let's do just a quick walkthrough.
Right. Yeah, I wanted to ask you, and the example that you have, you said k it's equal to 10, right? In this case, and the kth smallest element is for the matrix example that you have, it will be the 10th element from the sorted list, right?
Yes, I have modified my example. So
okay.
So yes, but I think for clarity, we should specify this. So thank you for bringing that up. Let me get my example right. So yes, you were saying k. So if k is equal to 10, what would be the kth smallest element, right? So that is not going to be 16, because we have these additional elements out here. It'll probably be 12 or something like that. I have to put it down here.
Right.
We can actually, but this is a very good exercise. So let me do that. So if we'd have -2, then 1, then 4, 5, 7, 9. Then I have 10, 11, 12, 10, 11, 12. I have 13, then 15, 16, 17, 18. Okay.
Right.
For them all. So the 10th element is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it'd be 13. So in this case, it should be
right.
13.
Perfect.
And then this is here. Is that okay?
Right. Yeah, I just want to make sure that we're in the same page. The understanding. So thank you. That's
good. So we now want to improve on this space complexity and time complexity. So here, what I see is these arrays are actually sorted. So what if we could leverage that information to improve on our complexity? So now we know that the first element of each row is the smallest element. So -2 is the smallest here, 1 is the smallest, 10, 12, 16. What if I were to take all these elements, so 10, 12, and 16. Now, we also know that these elements are sorted this way. Okay, we have another person joining. Okay, good. We also know that the elements in a column are actually sorted. So you could actually say that the element at 0, 0 is going to be the smallest element in your entire matrix.
Right.
So now we're just going to we're actually going to initialize our minimum heap. So we're going to create so the first step, what I'm going to do is I'm going to take a min. So this is going to be my min heap. And in this min heap, I'm just going to initialize it with these first elements of each row. Okay. And then what I want to do is I'm going to do a couple of things. I'm going to work through my heap and keep popping the smallest elements. So basically what's going to happen is I'm going to pop -2. So this one's gone. And then I know after -2, well, I have 4. This is in a sorted order because I do want to go in a certain order, in a certain fashion. So I don't want to leave any gaps in between here because these are sorted. So I'm going to, since I have, I popped -2, well, what's after -2? It's 4. So now I'm going to put 4 in my heap. So I effectively popped 1 and I pushed 1. In the next iteration, I'm going to do another pop. And, with the minimum heap, it's going to give you the smallest element. So in this case, it's going to give me 1. So I'm going to get 1 here. Now let's look at this. We know what comes after 1 is 5. So I'm going to push 5 here. All right. Next iteration, I'm going to do a pop. This time I'm going to get rid of 4. And here comes 4. Well, you get the idea. So what's going to go here is a 7. All right. So here comes the next iteration. The smallest element is going to be 5. So I got 5 here. Well, next is 9. So I'm going to get rid of 5 here. Do that. And here comes 9. Okay. Now the next iteration is let's get the next smallest element. Well, it's 7. Well, after 7, we have nothing. Okay, so we don't have anything to push. That's fine. So now the next iteration, get rid of this, we have a 9. Okay, so we got 9. Let me pop. So we have pop 9. And I look at 9. Well, there's nothing after 9. That's fine. So we go here again. And now I have a 10. So the number 10, we're going to pop 10. Okay. And then I see that after 10 is 11. So 11 is going here. Okay. Are we at 8? 1, 2, 3, 4, 5, 6, 7. Okay, almost there. So the minimum number here now is 11. So I'm going to take 11 here. Okay. And then what comes after 11 is 13. Okay. So here I'm going to pop, I would pop 12. And so here's what we have. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And well, let's go one more time because we want the 10th smallest element, right? So we are at 9. So you will see what happens here is you got the minimum, which is 13. Okay, get rid of 13 here. Now, I don't know, I was not keeping track of whether the 13 came from here or here. So that's something that we would need to remember when we are coding. We are going to assume that it came from here because these are the smallest elements. So there was nothing there to push. Now at this time, it doesn't make sense for me to go and do any more work because I have got to the magic number of the number of elements, which is 10. And so this is my answer and I would just return 13. So we want to optimize and that's how we've done this. So now let's see. I want to evaluate this for the space complexity and time complexity. So let's see what happened to our space complexity. So from a space complexity perspective, we have this minimum heap. And you can see at any point of time, we maintain a minimum heap such that the number of elements in the min heap is always being maintained less than or equal to the number of rows here, correct? So you have an n, so it's always less than or equal to n. Okay, so the maximum, the space complexity would be like we have about n elements here. Okay.
Right.
Okay, so that would be our space complexity. And now let's look at time. Oops. Let's look at time complexity. So in time complexity, let's talk about what the amount of time it takes to delete an element from a minimum heap. And we discussed this, it's basically going to be O log n. Because just the way the algorithm works is you delete the root element, and then you have another element that has to work its way up through the tree, through the root, so that the basic premise of a heap is maintained. It is in the case of a minimum heap, the value at the parent node has to be smaller than the value of its children. Okay, so the time complexity is going to actually be for if you have to delete just one element, it would be O log n. So if k was just one, but then if you have additional elements, we're going to work to the minimum heap k times, and so that's going to give you k. It's going to be O of k log n. So let's contrast the two. So this was before. I'm going to say. So we've got the brute force. It's going to give you this much. Then this, we have a new, the new solution is going to be, so we are actually going from space complexity O n squared to O n. Now the time complexity was k log n squared. We're going to a time complexity of k log n.
Yeah, a lot faster.
Yeah. So,
instead of having this polynomial time complexity expression, you have just a simple expression, which is much more efficient. Okay.
Right. All right. So I would like to just briefly put down my algorithm. So a couple of things that we noticed. I noticed when I was walking through this algorithm was we need to keep track of. We need to basically iterate through each of these arrays, and as you're iterating through them, you have to be careful, and watch out for when you have reached the end of the array. So my algorithm would be, I need to have an iterator over each of these arrays. So for that, I would actually create a list of iterators. So I could say sorted, this is my sorted array. I would have an iterators, and I will be using, I'm using Python. I would just do like a list comprehension. I would say iter, I'll call an x, and for x, so each of these arrays in matrix. So I would actually initialize this to this. Then the second step is I have this, the min heap. I'm going to be using the min heap. So the min heap is actually, it's going to be storing something, but I also know that, like, for example, you have a 13-year and 13-year. I can't just store these values directly in my min heap. I need to have this additional kind of metadata that will tell me which row it has come from. So I'm going to use a tuple I will store tuples in my min heap. So the min heap will be, it's going to be a tuple, and the tuple will consist of 2 integers. So one integer, of course, it will be the actual value, for example, 13. The other integer is actually like an index. It's actually like your row index. So 0, 1, 2 in this case would be 13, 2. And so this, I would just, it's initialize it. I'm just going to make it empty. And I'm going to be using, for Python, you have the heapq module. Now, once I have this, the next step is I have to heapify. So heapq, I would heapify my min heap. So I would actually do that. I can see that I'm coding a lot here, which probably in the interest of time, I could be doing it here. So I'm just going to talk through a few steps here. So similar to what we're doing here, it's just while I would heapify this, then the first step would be, I'm just going to populate my min heap. You could see I'm actually initializing it with the first elements from each of the rows. And the next step is going to be where all the magic happens. We start iterating, we start working our way through the min heap to get the smallest element. So with that, I would like to get started with the coding. I've done some coding right here. And in the interest of time, I'm going to actually copy it over. So let's do this. Let's get this up here. Okay, so we got heapq. All right. So these iterators are going to be our friend. They are going to help us work our way through each of these sorted arrays. So we've got the sorted array iterators. We've got this. We've got our min heap, and we've heapified our min heap. Okay. So let's say step 1. We're going to store the first elements of each row in the heap. Okay, so how would we do that? So we know we have iterators, right? So I'm going to do something like this. So for I, it in enumerate. So I'm going to enumerate over the sorted array iters, okay? And here's what we'll get. So I'm going to get the first element, right? So the first element is going to be equal to the first element, and yeah, the first element will be equal to, I'm going to do a next on my iterator. And when it comes to iterators, you have to be careful just using the calling next, because if your iterator has been exhausted, like it's come to the end, past the end, it will throw an exception, like stop iteration exception. And we don't want to break our control flow here. So what we can do is, when we call next it, I'm going to pass in a default value of none. So if the iterator has been exhausted, the first element would actually be none. So I can actually check. I'll say if first underscore element is not none, okay, then I'm basically going to do a min heap dot heap push. Okay, I'm going to push. So sorry, let me fix this quickly. It's heapq. It's heapq dot heap push min underscore heap. And now we want to store the tuple. So we talked about this confusion here. You know where the 13 came from. So I want to store a tuple. So the way I'm going to store it is I'm going to store first element, this value here, And then this is going to be that index. Okay. And that is pretty much it. Just go with it again. So we have for I, comma, it, this is enumerate. I'm enumerating over this list. And because I do want the index, I do want the value. And so basically this is, so in the case of this one, for the first row, it's going to, the next will actually, the iterator is actually going here. For each one of them, the iterator is actually, is actually moved forward. So we should be having -2, 1, 10, 12, 16 in our min heap. So this is good. So this is just our first step. And now is the second step. So we are going to, we will actually pop, we'll do a series of pop and push steps until, rather I could say I want to perform at least about, you could say actually k -1 pop push steps. We'll see. We want to actually basically just work our way through this minimum heap, popping off the first k -1 elements. Okay, so here's how we would do this. So we talk about the minimum heap as a queue. So here I'm going to do while min_heap. So this gets interesting here. So while min heap, I'm going to get my smallest underscore element, right? And then I'm going to get the smallest underscore element underscore I is equal to heap q dot heap pop. And here I'm going to get my min underscore heap. Now remember, when we pop this, we're actually getting a tuple. So here, what's happening here is we're getting the tuple. It's an unpacking of the tuple. So you're effectively just getting that value. For example, we'll talk about 13 and 0, 1, 2. So you will get like 13 and 2 here. Okay, so I've got the smallest element. Now the next step is, once I've popped this element, as we were working through this, we said if I've popped like -2, I need to advance this iterator to the next element, right? So first of all, I need to get that iterator corresponding to this particular row. And this is where this index is going to help us here. Okay, so what we'll do is, I'm going to say the sorted array, this is singular, iter, is equal to, I'm going to index into my iters, and I'm going to use my smallest element. So this is my index, okay? So effectively, so I've got this particular iterator corresponding to this particular index, okay? And then I do want to get that next element, you see? So we talked about, okay, -2 is gone, and then I do want to get the next element, 4, which I will add to my min heap. Because we always, you can see that with each iteration, we'll pop the minimum element and we'll push like the next element. So now what I'm going to do is, I've got this iterator and I just want to get, what is that next element? Okay, so this is my next element. So the next element is going to be, let's say, I'm going to say next on my iterator. So this is my iterator here. I'm just going to be a little bit lazy on this one. Now, again, I want to be careful here, because if this iterator has been exhausted, like we saw in the case where it became, okay, maybe we were at 7. If it's exhausted, it's going to throw an exception. So to avoid that, just to maintain this control flow, I'm going to specify the default value of none. Okay, and then I can have my guard code here. If next element is not none, then what I'd like to do is I would do a heap q dot heap push this next underscore element. Okay, now we also said that we just don't want to keep on pushing and popping all n squared, do it like with an n squared times or whatever. we realize we just want the kth smallest elements. So I'd like to use, so we can use something like a count. Okay. And let's see, I can do a count. Oops. That's equal to 1. And so while I'm in heap and count is less than k. So that means, let's say if k in this case, which was the example, k is equal to 10, and I've executed this 9 times, and now count is now 10. Of course, it's going to break out of this while loop. And then, so 0 to, actually it's going to be 0 to k minus 1. So actually, it's going to actually run through this. It should have run through this at least k minus. I'm trying to catch myself here. It should have run through this such that now we should be at the kth element. So return. So I should have my. And I will verify that. Make sure this is okay. So count equal to 0. So count 1, 2, 3, 4, and it should be.
Yeah, I think you are correct. Because when k it's going to be, k is going to be like your example is 10. Yeah. So and you're exactly executing 10 times. So when count it's equal to 10, then it's going to break the loop. Okay. And you will be with the smallest element.
Okay. All right. So I'm just going to just walk through this quickly. Well, this in terms of, I'll first talk about the space complexity. Space complexity is, here we are storing, the worst case is going to be ON. Then here, so we have some space complexity here as well. But those would, here too, we are storing this. So this is again O of n for n rows. So it's really n plus n. It's still going to be
right.
Right. For the time complexity, well, we have like n iterations here. So time complexity, we are doing about n iterations here. And then, of course, here we've talked about this one. The time complexity is going to be, we're going to do k times. We are doing this, the push pop, and these are all log of n.
Because you are using the heap, right?
Yes.
Yeah, instead of having to traverse all the whole every row, using the heap, you just have to insert the k number of elements at every iteration. It's okay. Yeah.
Yeah, it's actually the heap
just one n.
Will always have a maximum of n elements.
Right.
So then the heap operation is going to take us log n, but we are going to be working through this k times because we want to work to the kth smallest element, and they are in sorted ascending order. I am going to check for any typos. And
I think I saw one in the line 16. I think you're missing just an I in the name of the list. Sorted array iters in the 16 line.
Okay.
Yeah.
Yes.
Yeah, you're missing an I.
That was a good catch. Very good.
That's the one. I just spot that one.
Yes.
I think the rest is it's fine.
Yes. Okay.
Line, okay, Michelle, she says that the line 28.
28.
No, okay, maybe you can clarify, Daniela. So in this case, you're using the sorted array iter, which is not the iters array, right? Because you are using just one of these elements in your, exactly. Maybe that helps to
Is that more readable?
without, exactly, yeah, because thank you, Michelle. I think that makes the code a little bit clearer, I think.
Mm-hmm. Shall we take it for a spin and run this?
Yeah,
Okay.
you can go ahead.
All right. Well, let's do this. Oh. Ah. Yes.
Okay.
Yeah. So this is important. So remember the heap. We don't just store the element. We are actually storing a tuple. Correct.
You're right.
We have to remember that this was a typo. You have to store the element, like we said, 13, and then that particular index. So in this case, it would be 2. So that's what happened here. And also this is missing. I think it was in a rush. You have to pass your min heap, and this is the value that you push.
Oh yeah.
So the heap pop is just you're popping off the min heap, but for heap push, you specify your min heap, and this is the tuple that you're putting on that min heap. So that was
Good. Yeah,
that.
very, very good. Okay, so that
And then
so you got it right. Excellent.
that's what it is. Description. And yeah.
So I just I don't know if we have time for some question, perhaps from someone of the attendants, maybe if they want to make some question. I don't know if you have any time check. Monica, how are we doing?
I'm just gonna stop the recording, and then we can